I'm from Stony Brook University, Love Center. So my partner, Troy, um, uh, who didn't come today, and I joined the D3R challenge for the conception for energy set. So I have two advisors, Professor Carlos Simelin, who is also known as a member of the Amber Society, and Professor Daniel Roddy, who is an experimentalist studying protein biophysics. So at first we use free energy calculation to study the effect of mutation on protein stability and the protein interactions. And we found the free energy calculation is a very handy tool when compared to experimental value. And I developed my own protocol, and then we come across this challenge, and we just thinking to test our protocol and to see how alchemical free energy is compared to other methods. So, yeah, so this in some outline. So the first part is just what we did, and the challenges we think free energy calculations are facing, and how to overcome these challenges, how to perform successful free energy calculations. So I will describe the way I did to overcome those challenges, the layout protocol, and I will show the result. And I will share with you what we've learned during the challenge. And then it's just general introduction on those most recent development in free energy calculation that I think has made free energy calculation very different from what it used to be. And yeah, in the final part, it's yeah, about to get students started using free energy in a much easier way. So I just from a user perspective who's been using free energy calculation for years. Um, just some introduction of the free energy calculation. So we know that there are like three major methods for computing the delta G from state A to state B, right? FEP, TI, and bar. So we use thermodynamic integration, and this is the derivation for the thermodynamic integration. So you can see it's based on statistical mechanics, everything is physics based. And in the end, what we are calculating is just this equation here. So X is the coordinates, a very simple equation. X is the coordinates, U is the potential energy function, and we have a bracket which indicates that we need an ensemble averaging obtained from MD simulation. And since it's physics based, so we do not need any existing affinity data. So this is different from machine learning and statistics based method. And so that means it's just transferable between different systems. So yeah, So when people talk about relative binding free energies, they will always refer to this kind of thermodynamic cycle. So red arrows are measured by experiments. So it's a process of binding and unbinding. This is slow dynamics, which cannot be modeled in MD simulation. So but thermodynamics it depends on states instead of processes. So what people do is they calculate the changes of the free energy change from one ligand to another in the complex state and in the free state. And then the difference between these two blue arrows equals the difference between these two red arrows. That's how we translate the calculated delta G to the PKD here. So everything, it seems all we need to do is to just get this simple equation estimated, right? So what's the challenges here? The challenges here is just we need to get every critical components here correct, including this one on the left side. So for example, like those challenges in that free energy calculation are facing are that people need to design a reasonable transition pathways, right? So a pathway that's short and neat and provide the most, maximize the phase overlap of phase space. So this is usually just done by trial and error. There's a rule of thumb, but there's no gold standards people stick with. It will differ from people to people when they design these transition pathway. And also U, which is the potential energy functions. So this is just depends on the quality of the general atom force fields. And also X, which is the coordinates of the protein and the ligand. So so it also depends on the quality of the force fields. You just need to get the protein and the ligands stay stable and stay bound to each other during the simulation for enough time to get you, so you can get those averages. And the other one is just the bracket sufficient sampling. So it's just whether you have an accessible and inexpensive computers that allow you to do this in a reasonable amount of time. So these are all the critical components, but the equation is simple, but to get everything right is quite challenging. So first we come for the transition pathway. So everyone do that a little bit different. So yeah, so I think everyone will start with this. When they do relative binding free energy calculation, they just start with drawing out these kind of maps. They compare ligands and try to build this network. So what I did is when I'm doing this, I try to make it more parallel. So so I included some artificial ligands or artificial intermediates in the center of this map to try to organize stuff and make it more parallel. And then, so in some cases, when you go from ligand 1 to ligand 2, if the perturbation is too big, you may need to consider splitting the transition into multiple steps. So this is what people usually do, but everything here, so when I do that, everything over here will loop in my head a few times until I find a solution I feel comfortable with. So because it takes trial and error just to get this done. So everything, another thing to note is everything depends on the protocol, the TI protocol you are using, and that will again depends on how the code is implemented in the software. So I will talk about that later as well. So this is just zooming into the map. So the first thing is just to compare those ligands to find the similarity and then just group them into different groups based on their similarity. And important thing when calculating binding free energy, relative binding free energy, is just to get this map as parallel as possible to minimize the distance between ligand pairs on the transition pathway. So every ligand, just make every ligand pairs as closer to each other as possible. And the red one are those ligands not in the data set. I just added these to help organize stuff and make it more parallel. These are the structures. Then I will talk about the protocol. So ligand protein preparation. So I use AM1BCC to assign the charge. So this is the traditional one. So there's nothing too exciting about this charge assignment scheme. And I use GOV2, which is newly recently developed. And there's a lot of modification coming on to this new force field now. So, and also the protein force field, I use the one our group developed, FF14SB plus TIP3P water. So FF14SB is the first, is a force field that can fold protein on its own in implicit solvent. So it promotes protein stability a lot in this version of force field. So and the MD simulation protocol, just regular MD simulation, you can find in tutorial. So and the 4 nanosecond, I will come back about this, the choice of 4 nanosecond here. And the different things I think here is I use linear scaling, single topology approach. So I bet nowadays I probably am the only person using it still, right? And so that means I'm not using soft core potential. And I will come back later with more detail on why we do that. And the lambda windows is just something given by Ember tutorial, and we have 2 more windows just to push the lambda into a value closer to 1. So overall, this is a very simple protocol. You can find in tutorial. So there's nothing too advanced here. But even with this simple tutorial level protocol, we still have a success in the challenge. So this just means that things are changing for free energy calculation. All right, so since we don't, as I just mentioned, we don't use soft core potential and we use linear scaling potential. So yeah, since we need to make a reasonable perturbation every step, just to so the DVD lambda is not fluctuating too much. So every time to remove this 2-oxo pyrrolidine group, we just divide it into 3 steps. Every time we remove just a little bit of heavy atoms every time to make it as less perturbing as possible. So that means we'll have many lambda windows accumulated. So overall, we'll have 40 lambda windows. So if we are using soft core potential, this can be done in 1 step. But the take-home message is just no matter you are using soft core or linear scaling, just make sure you design a reasonable perturbation that the scaling scheme can handle. It doesn't matter what you are using, but it's important to design a good pathway that DVD lambda is not fluctuating like crazy. And the other thing is I think the D3R doesn't, for the free energy set, doesn't give us like a reference PDB code people can use to run the MD simulation. So I scanned a lot of PDB code that has cathepsin S with similar ligands. So we decided to use this PDB code, and it had 2 chains. So one chain A and the chain B. So the difference between chain A and the chain B in this PDB is that it's over here, the nitrogen, the conformation of this pyridine group over here. So in chain B, so if we protonated this pyridine group, the proton will be pointing towards the solvent. But in chain A, the proton is pointing into the protein. So since the proton is charge carrying, pointing towards solvent is much favorable than pointing towards a protein and get buried, right? So we choose this one. So this is just some minor things, but very important for free energy calculation. So this is our scaffold. We didn't perform any docking because all the ligands are very similar to each other. So we just adjusted things manually when we add and remove atoms, and we do minimize before MD simulation, and then we let MD simulation take care of everything. So we also scan just to use all the knowledge present in the available to the public. So we just scan all the X-ray structures available and determine the binding, the conformation for those functional groups we added and modified. So yeah, so in chain B, overall, we will have 2 pi cation interactions forming between these 2 charge carrying proton and this phenylalanine. And as that's just chain B has a tighter bond to the protein than chain A. So these are our, just want to explain what's happening with why we have 4. Okay, so these 2 are exactly the same, but just submit under different name. These are as well under different name because tri-9 has different affiliation. So, and then this is our original calculated, but we are very uncomfortable with the fluorine Lennard-Jones potential. So we just say, oh, let's maybe just make a empirical adjustment here. So it's a very small one and almost does nothing. Okay, yeah. And this is the matrix for the correlation and the centered MSD. So I think it's a successful calculation. So back to the transition map here. So so this map is reasonably parallel, but it's still not the maximally parallel one. Still we have a serial fashion of connection between different group of stuff. So what we are interested in is if these are a little bit of serial transitions. Do the arrow between the transition between do the arrow of the transition between these intermediates get copied into the ligands between different group? So this is an issue also in. So this will be an issue if you have a more serial fashion map. So what we do is we construct a heat map. So blue is high accuracy, red is low accuracy. So it's a pairwise delta delta G arrow. So we have 39 ligands, so 39 times 38. 39 times 39 little squares we see here. So the values encircled in this yellow region is delta delta G for ligands coming from the same group. So what we do is just compare delta delta G, accuracy of delta delta G within a group which is highly parallel to other groups which has a kind of serial connection. And it seems like within a group and outside the group doesn't have too much difference in accuracy. So that means we have some, it's not maximally parallel, but it's still okay. This error is not significant, accumulation of error is not significant to show anything weird. So another question I get asked a lot about this kind of protocol is, since you are doing linear scaling and you have a lot of intermediate states, that means you have a lot of transition states. So do the error or uncertainty in those transition steps get accumulated as you sum up all the delta G, right? So this is a good question. I actually don't know. I'm not quite sure. And so I did this analysis. We'll have analysis with looking at the relationship of number of transition steps with the arrows we get in pairwise delta delta G value. It seems as we have more steps, the arrow goes up a little bit, but it's not too huge. So in conclusion, I don't think number of transition steps in this case affect accuracy a lot. So to my knowledge, I think having a lot of transition steps or intermediates, it's kind of okay as long as the intermediates is right on an optimal transition pathway. So yeah, that's just my opinion. So this is the histogram and the cumulative histogram of all pairwise delta delta G arrows. So this is all pairwise. So 39 times 38 divided by 2 pairs. So you can see everything is below 2 kcal per mole. So pretty amazing. And 84% of it is below 1 kcal per mole. So that's pretty high accuracy. And also just to give you a sense of the uncertainty I got, or the standard deviation I got for each independent run. So for a ligand pair, usually I got in standard deviation below 0.2. So of a 3 independent runs. So I will consider this kind of standard deviation a safe one. And there are a few over 0.2. It's just because they have these ligand pairs have a larger difference, so maybe 6 heavy atoms. Right. So just a few thoughts that we have learned during the challenge. So actually, we think longer simulation do not necessarily help a free energy calculation. So this is very different from like other studies. Always people will tell you if you are using MD simulation, just extend the run, to get better average. But from what I read in all those publications. I think 4 nanoseconds and 5 nanoseconds is what I usually see people using. So the reason I choose 4 nanoseconds is because it's just enough to relax those amino acid side chain on the surface of protein. And the problem with extending the simulation is that the protein will start to unfold or misfold, and the ligand may come off the binding site because of those small errors in the force fields. Those errors will accumulate during the MD simulation, and you will find a weird conformation that has nothing to do with the binding. And if you just run it long enough, protein always get unfolded, right? So another thing is in some cases we'll have very slow changing or slow dynamics but still very important to the binding, like the very notorious valine 111 of T4 lysozyme. So in these cases, we can use local sampling enhancement techniques, which just facilitate the arrangement of those side chains around the ligand, but still keep the global structure cool and stable. Yeah, so there's technique we can use. So just to stay with, in my opinion, just to stay with a short time during a simulation. Yeah, so algorithm like REST. Yeah, that's what you can use. So this, I'm not so sure of these slides, but I think TI saves more storage space compared to FEP and bar. So I think I remember FEP, if I remember it correctly, bar and FEP require post-processing. It can be done on fly, but if you need to add more lambda windows and get a new spacing, then you will have to do the post-processing again. Then you have to pull out all the trajectories. So bar is, you might need to save some trajectory just in case you are changing the lambda spacing. But TI, I never worry about saving trajectory because it's not, it's do the DVD lambda calculation on fly. So I just save like 100 frame of trajectory for each pair of ligand. And only DVD lambda is collected. So overall, I just have 180 gigabytes of data. And if using bar and FEP, if I save just everything, there will be 25 terabytes. So a huge difference. Of course, you can discard it and just run the same thing again later. So back to this one. So back to why I'm using linear scaling single topology versus soft core potential dual topology. So we know soft core potential allows larger perturbations in a transition. So it's by all means superior to linear scaling. And the dual topology is easier to set up than single topology. And so these two combined together, soft core potential, dual topology, they are just more efficient than linear scaling. And this approach is used predominantly today instead of linear scaling single topology approach. So this is what makes it different. So in single topology, you can only go from a larger molecule to a small molecule that has all atoms covered by the larger one. And in dual topology, you can handle many different chemistry just in one topology. It doesn't matter you are going from a larger one or smaller one. But we found that the soft core potential dual topology approach in Amber TIs has some issue, just like people have mentioned yesterday. The unified decouple scheme give different results. So we've so I've known this for many years, but when I brought this up, people didn't believe me. At that time I'm just second year PhD student. And I really appreciate this conference. At least my words get heavier now. So so this publication is people can check this one to see what's the detail. So soft core dual topology in TI is what's wrong with it? It doesn't allow scaling of bound angle dihedral 1,4 van der Waals electrostatic interaction between the changing part and common part. So there are two levels of issues here. So one level is not allow scaling bond angle dihedral, and the other more serious level of issue is not allowing 1,4 potential scaling here. So Amber has already fixed some of them. I remember 1,4 is already fixed, so it's safe now. So not allowing bond angle dihedral will be a problem for some transitions. So it's fine for most of the transitions, but for some transitions like sp3 atom to sp2 atoms, there will be a problem. There's a lot of publication discussing this issue. But on the other hand, linear scaling, single topology approach, it just allows scaling of everything. So I can scale whatever I want. So I don't need to be worried about that something is not scaled and I'm not aware of it. So we use this one, even it's inferior to subcore potential dual topology, but we are 100% sure what we are doing. We feel very safe doing it this way. So it seems like this may not be just Amber unique stuff. So just a publication coming out at last week in NAMD. So people found this kind of, I think it's kind of the same issue. It's also about not scaling bond angle and dihedral in the interfacing region. So they use hybrid single dual topology. I mean, by the name you can tell they just combine these together. So they allow the software to scale those bond angle and the dihedral they think they need to scale. So my conclusion of this is it's important for the user to know what the code is actually doing. Or we have to get people together to figure out infrastructure, a unified infrastructure that's good for all the package. Okay, so this is just about Phrenology, the progress. So now we start about the progress in Phrenology made in recent year. So I think when people talk about alchemical Phrenology, they always think it's expensive, slow, inaccurate, and not worth trying. And overall, it's a thing for academia. And even D3R has this statement there. So, but from my experience, alchemical Phrenology calculation has already changed a lot, and it's not what it used to be. All right. So one of the biggest barrier that's there is people's stereotype. You know, people just not willing to try that and to try to invest into the development of more useful techniques. So I will try to convince you that what have changed alchemical Phrenology in recent years. So many stuff are just like this past 1 or 2 years. So still back to this one, as I said, this is very critical. We need to make everything critical here, correct x coordinates, U potential energy function, and then ensemble averaging. So these are all already improved a lot. So one example, for example, the protein structure. All right, so in our lab, we develop amber force field. So James Mayer is the developer of 14SB. And he and Hai conducted long-time simulation in implicit solvent without restraint. And they can fold a lot of protein on its own. All right, this is without restraint, a pretty remarkable accomplishment. And what they changed it in 14SB is that they apply sidechain amino acid specific sidechain corrections to each amino acid to make it more like a quantum mechanics. All right, so yeah, so my friend Chuan Tian, he's following up this project by applying, even giving it more corrections on the backbone torsion angles. So this year we have 19 SB coming out. So this further increase the stability of protein, so the protein doesn't enter a weird geometry that's irrelevant to binding during the simulation. All right, so this is his result. What's remarkable here is we have, when you look at the predicted and the NMR measured helical propensity, so this is the result from the previous generation of force field, 14SB plus TIP3P. And this one is the one we just developed like a few months ago. We published a few months ago. That's 19SB plus OPC. And you can see we have a good correlations in the previous version, but we got a much, much better one correlation here. And to get noted that, 14SB is not trained against these data, and never sees experimental data before. And the OPC also, it's not something for improved helical propensity. It's just trained against physical property of liquids. So with all these, we are matching the experiments better by just making things more like quantum mechanics, I guess. And so this is regular MD simulation of model protein to see the stability of the protein in the simulation. So you can see overall 19 SB plus OPC water model, they are getting the protein to a lower RMSD, which means protein are getting more and more stable in this after all these kind of corrections on the force field. And then note again, this is not all this, the force field never seen this before during the training. And another improvement is the potential energy function of the small ligand. Now we have GOP2, which is more diversified, which have more diversified atom type and specific Lennard-Jones bond angle dihedral for different chemistry. In the future, we'll have open force field and with even more diversified chemistry. So, and we also have machine learning trained on DFT like A9, which will give us a quick estimate of QM energy that we can use to correct those force field. GPU, I guess everyone knows this. So this, so Ember TI has get a huge boost after using the GPU hardware. So everything can be done in a very cheap and fast way now. So now this is the estimate I have for doing this kind of calculation. So for a size of cathepsin S to 21,000 waters, including the protein. So if we are using 16 GTX 1080 Ti GPUs, it takes 1 to 1.5 hours. So it's still, still a huge investment. But, so if we map it to the financial cost, so I checked out recent cost of leasing this GPU. It's just $0.12 per hour. So it just takes us $2 to do a pair of scan on using free energy calculation. And these costs include all the hardware maintenance and then electricity. You just pay the licensing fee and the networking fee. So and this is my estimate. I'm using linear scaling, so if people using more efficient algorithm, this will get down like much lower. Okay, my estimate is it can go like 1/3 of these costs if using other protocols. How much time do I have? Okay. So I also working a wet lab, so I know what $2 can buy now. 5 pair of gloves and a 5 50 ml Falcon tube, and this is 20 pieces of tissue paper, not 20 package, okay, and 20 pipette tips. So consider that, would you rather do a calculation or really go to the wet lab to do the scanning? So free energy calculation is not perfect, but think about the cost, okay. And one of the biggest issue I think for free energy calculation before is scaffold hopping. It's just any chemical changes involving bond topology change. So like this one, we have to break a formal bond here. So what for cathepsin S data set, D3R just gave us R group modification. So those just modification on the edge of the molecule. So the base one, they selected compounds with lots of different kind of scaffold hopping. So usually, this is considered not doable, and sometimes we have to use absolute energy calculation, which is quite not easy to do. And actually, scaffold hopping can do a lot of things and very important in drug design. So it allows more chemistry space and a patentable drug and side effects, avoid side effects. And one more thing I like is that allow people to utilize entropy in addition to enthalpy. Okay, so but these are very hard to synthesize. So it needs computational prediction more than those R group modification compounds. Yeah. So so there's these are the things developed by Schrodinger, which allow different kinds of scaffold hopping. So ring extension, which you attach another ring onto a existing ring, and forming and breaking a ring, and also contracting and expanding a ring. So these are if they are using their techniques, they can do relative binding free energy with a higher, with a more overlapping in the phase space. So this is one of their advantage. And I think there's more efficient sampling in the lambda space. We have, I guess, a lot of software package is allowing lambda space exchange using Hamiltonian potential exchange. This will be, I think, will be a norm in the future. So minimal trade-off of speed, but a huge gain in the convergence rate. And we also have lambda dynamics. This is not a recent stuff, but I think will be a huge thing in the future, because these allow high throughput screening of compounds. And so Ember is having new features. So which it's a method to optimally put lambda values at where it should go. So it will have combines metadynamics with those Hamiltonian potential exchange. So it converge more quickly, and overall will have a 3- and 4-fold speed up. So if you use these techniques, those costs, those time costs and the financial costs I just gave will be lowered by another 3 or 5 folds. All right. So the result is just a continuous spray of the lambda window. So it goes to, it just covers everywhere. So usually, if you have discrete lambda, you probably will miss some of the DVD lambda that's changing rapidly here. Right, so this is one of the advantages, and they just converge much faster than those regular replica exchange method. So we'll be in the Ember in the future. And constant pH, constant redox potential. This is, I think these are very essential for the base one data set, right? It will be in all the major software, I guess. And one of the things I like a lot is this water partitioning. So it allows solvent to get into a barrier site much easier than before. So I guess the people who write there, I saw him yesterday. So it will be in Ember also. Yeah. Already? Okay. All right. That's great. That's fascinating. Yeah. Things are changing. And things are changing a lot. Do not have the stereotype. Yeah, and one last thing is, as a user, I have a lot of failure in doing free energy calculation. I have to figure out myself. So one of the things I feel about alchemical free energy calculation is it has a very low error forgiveness. Everything must be perfect to get the result. Like for example, the choice of the binding, choice of the crystal structure, right? If you choose the chain A, you start the MD simulation, the ligand just come off right away. This will not be a problem for if you are using static model, right? It just stays there. So this is what make another challenging free energy calculation is facing. So an option is to have a very intelligent automatic workflows that just take care of everything, make high level judgment. And another option is, of course, just to teach our students better, to let them know the limitation. So I feel like a lot of tutorials, manuals about alchemical free energy calculation, and teach people how to get the delta G. It doesn't teach them how to fail. They didn't know the limitation of the free energy calculation, so they assume they are doing right, but they actually are not. So I think it's important to teach students, like have a program or stuff like that to teach students how to fail. Yeah, I'm developing something. So this is still under development. It's just a scratch kind of things. I don't know how it should go, whether it should go to like a workflow of that kind of stuff, or a more educative and instructive script for helping students get started. So maybe during the later discussion, we can talk about that, how to proceed with that. And in the end, yeah, thanks again to Chuan Tian, who helped me with this, did this calculation with me. And thanks to my advisor, all the members, and thanks to the funding and the Love Center. And thanks to those who administrate the computing cluster, and thanks to D3R and all the participants. Yeah.
Do you want to pass? Oh, maybe you'll just have a repeat. Or do you want to?
Yeah, I will repeat.
Yeah, let's do
All right, so I have that was really nice. I really enjoyed it. A comment and then a question. So the comment is also an advertisement. So we have a journal that has a new journal, Live Comms. This book has a category specifically on lessons learned. So stuff like how to fail. So if you're interested in writing up any of your lessons,
Okay.
along those lines, there's a category specifically for that, because we think you're right that there is a gap in how well we educate people on that. The question is about linear scaling. So as I recall the work from the 90s, with linear scaling, there's a non-integrable singularity at the end state in TI. So my intuition is that what that means for your calculations is that you have, you're deliberately keeping the transformations small, which probably means you're avoiding a lot of the errors, but you're probably accumulating a small non-zero error each time from sort of a neglect in changes in sterics or effective size of the atoms. Have you looked into that at all? And are there any plans with Amber TI to implement softcore for the single topology protocol?
Okay. Yeah, this is a very good question. So yeah, in previous slides for the Lambda windows, I do. I do try to make, approaching one more. Yeah. If I just set lambda to 1, it will fail. Yeah, but so it's an approximation. So So this protocol, I use these for many years. So we use that protein for studying protein, and we got good result compared to experimental results. So I'm very confident at this protocol. Even it's not perfect, but I think this kind of level of approximation is still like not a very notable things. So you are right. This is not a rigorous one, but we tested and we feel comfortable with this protocol.
Are they implementing software for the single topology?
That I don't know. I'm not sure, but Tyson is planning to fix these. He's aware of these issues.
So I guess if you were comparing it to like a calculation in Romax or something of the same transformation, you probably accumulate like 0.2 to 0.4 kcals per molar each time you do it. So it's not something you probably see relative to the experiment. It's just there.
Yeah.
It's about and it should get back out.
Okay. Yeah. Okay. Yeah. That would be nice. Yeah. Yeah.
You just said the long time simulation is not necessary, right? But if the simulation is not long enough, according to my understanding, how to guarantee the probability result is converged or not?
Okay. This is a very good questions. Also, so to do fringe calculation, in principle, you wanna to minimize the fluctuation of the UD lambda, and if so, my understanding is if you have a high dVd lambda, that's you just a high fluctuation of dVd lambda. Maybe there's a problem in the pathway you design. Instead of just letting it run, force it to converge, getting an average. Just maybe just try to design a better transition pathway with low fluctuation in dVd lambda. So that's my solutions to that. Yeah.
Maybe I'll ask you here. A couple of things. So first of all, I think it's great work that you worked around with it.
Maybe use some extra letter. Yeah, let's do it. All right. Thank you. Steps. That's right.
Great. So yeah. Anyways, I think it's great that you worked around this that way with this. When you're scaling and single topology. Did you try the dual topology with the decoupled scheme? Because, like, for example, and also when you showed SAMs, like we also love SAMs, it's a great approach, but that exact thing where you showed where there was big dip was just a consequence of the unified scheme. So even with SAMs, you're still getting these fluctuations because the unified scheme and the soft core have a problem, with the van der Waals and electrostatics where you get atoms on top of each other. So I think it's great that you worked around it, but I'm not sure whether it's necessary given that you can use a dual topology decoupled scheme.
Yeah, so I've dropped dual topology like a long time ago. I never come back to that. So I just feel uncomfortable with that because I think this is fine. So I just rely on my protocol. And I think Ember has it's a two level of issues. One for interaction not getting scaled is a huge mistake we made before.
Yeah, Tyson's taking care of that now.
And this huge dip, I think, is if for unified and decoupled. So you turn off the charge first, right? In decoupled.
Yeah.
So but that means one for van der Waals interaction is still not scaled. You are safe with the one for electrostatic, but one for van der Waals interaction is still not scaled. So even there's a difference between unified and a decoupled, but it doesn't mean decoupled is correct. No, it's still not scaled. So I'm not too sure about. Tyson also mentioned this to me, but I'm not too sure about if he changed things or if it's still as before. So I'm not too sure about this.
Yeah, I think it's all in the current code now, but it's great that you worked around that.
Yeah.
So in one of your example of sub-intermediates, you have a pyrrolidinone ring that you break partially. So you have to be a bit careful when you do that because you're changing the non-bonded pair exclusion list. So I wonder if there are any particular tricks in Ember that allows you to get away with that, or if there are no tricks, why you felt it was a safe thing to do.
So you're asking about the scaffold hopping stuff?
No, so I think earlier in your talk, when you talk about sub-intermediates, you have a pyrrolidinone ring that you have to get rid of.
Oh.
You do that in several steps.
Oh, okay.
First step, you break a bond
Yeah.
inside the ring.
Yeah, so I don't break the bond inside the ring. So because the whole ring will disappear in the final step, so there's no need to break the bond because I'm just disappearing the whole ring.
So, but what do you mean by the sequence of sub-intermediate states then that you've shown?
Oh, this is alchemical drawing. So there will be bonds connecting those atoms, and it's just turning off charge and van der Waals interactions.
So you mean you don't actually care that the chemistry makes sense?
Yeah,
Okay.
yeah. Sorry.
Can I ask just one question? One thing that I was surprised to see was that, or maybe this is standard, I'm not actually sure. At the point where you needed to sort of manually manipulate the pose because of sterics.
Yeah.
I mean, so my first question, just being naive and not doing these calculations myself, is that a common requirement with these calculations? I mean, I obviously find that a bit like worrisome if I was thinking. I mean, and I also wondered how sensitive then the results are to this type of manual manipulation, or if you have a sense for that.
Okay. To be honest, we are not drug design groups, so we don't know how to like a lot of how to make a good binding pose or sort of things. So kind of like manual adjusting is our only options here. But I think it kind of we are guessing those binding poses, so we are not sure. We just pick one that we are comfortable with, and we will let MD simulation to take care of that. And in some cases, if we are so unsure about the binding poses, we will first remove the groups using lambda, right? Turning off the interaction using lambda, then bring it up by turning on the interactions. So we hope things get, get out of the wrong positions. So this is one of the way we do.